Now let's take a look at a second titration problem and see how it differs from the previous titration problem we looked at. First things first, as always, I'm going to decide what type of titration I have. So I start with a 100 milliliter solution of 0.5 molar HF, and I recognize HF as being a weak acid. It's not one of the 6 strong acids, and it has a Ka next to it, which implies it must be weak. And I'm titrating that with 0.2 molar NaOH, which I recognize as a strong base. So this is going to be a weak acid, strong base titration. I like to get a general idea of what my curve is going to look like. So I'm going to have pH here, and then on the x-axis, it's going to be the amount of strong base that I add. I'm still going to start acidic, not as acidic during the strong acid. It's going to have a little bit of curve, it's going to go up, and it's going to plateau. So here is going to be my equivalence point. Now for a weak acid titration, the equivalence point is not at 7. That's only for strong titrations. Instead, I can just think about what range it's going to be in. For a weak acid titration, at the equivalence point, all of that weak acid has been converted into conjugate base. So all I'm going to have left at the equivalence point is some conjugate base. Therefore, my pH is going to be above 7 once I hit that equivalence point. So just giving that general range is still going to help me figure out if I'm on the right track when I'm doing these problems. Some other things that are interesting about my weak acid titration, of course, I also have my half equivalence point. And at the half equivalence point, that's where my pH is equal. Can't read that. That's where my pH is equal to my pKa, so it's good to keep that in mind. In this whole region right in here, we call this the buffer region. So once I've reacted just a little bit of my weak acid with some strong base, I've created some conjugate base, and so what I have in this region right here is a buffer of that weak acid and its conjugate base. So I should expect to have a buffer if I fall anywhere in that region while I'm working my titration problem. So again, it's just good to keep these little pinpoints in mind so we can make sure we're on the right track. Now I'm going to go back and I'm going to think about my questions, and just like in my strong titration, I think the best one to start with is the volume needed to reach the equivalence point, because then for all of my other problems I can figure out where they should lie on the curve and if my results are making sense or not. So I've just pulled out that particular part of the question that I want to focus on. What's the volume needed to reach the equivalence point? Well, once again, the first step is we need to write a reaction. So I'm going to start with my HF, and I'm going to react it with my 0.2 molar sodium hydroxide. Though once again, I can make life easy because all of my strong bases I can just represent as OH minus. I can't do that with the HF. He's not a strong acid. It doesn't dissociate completely, which is why I just have to write him HF. So HF plus my OH minus. Now I just think about, okay, what do acids and bases do? Acids donate a hydrogen, bases accept. So I'm going to end up with F minus and produce some water. And we're going to be using this equation again and again in our titration problem. So, like last time, I want to organize my information. I had 100 milliliters of HF. It's 0.5 molar. I don't know how much hydroxide I'm going to use, but I do know that it's 0.2 molar. These big M, molar, that really stands for moles per liter, so I'm going to go ahead and remind myself of that fact. I need to do a little conversion. It's always easiest to start with the number by itself instead of one of these ratios I have. So I'm going to start with 100 milliliters of the HF. First thing is I want to turn that guy into liters, because I don't see milliliters anywhere else in my problem. And then I say, oh, look, I have liters of HF, and I have this piece right here that deals with liters. So I have liters on top, my liters must go on the bottom. For every 1 liter of HF, there are 0.5 moles. Alright, so I've used those two pieces now. I've gotten to moles of HF. Once I'm in moles, that's my opportunity to switch over to moles of the other guy. So now I need moles of HF to go on bottom. I want to turn those into moles of my base, which is hydroxide. I look back here and I say, okay, this is a 1-to-1 ratio. And now, getting close, I want to get rid of those moles of hydroxide. And if I look up, I say, oh, okay, here's this piece that deals with moles. And for every 0.2 moles, there's going to be 1 liter of hydroxide. So I just flipped that conversion factor, which I'm always allowed to do. So now I say, okay, I wanted volume. I've ended in a volume unit, so I do the math on that, and I figure out that that's going to be 0.250 milliliters of hydroxide. Though I like to put it, oh, I'm sorry. No. I'm still in liters of hydroxide. I like it to be in milliliters, so I'm just going to do a quick conversion. There's 1,000 milliliters in a liter, so that's going to be 250 milliliters of hydroxide. And so now I know the volume needed to reach the equivalence point. So I can go back and make a little note of that. It's going to take 250 milliliters of sodium hydroxide to reach the equivalence point. So that's going to be right here. That's going to be 250 milliliters. Now, just like I did with the strong one, every time I'm trying to answer another problem, I'm going to think about, okay, am I before, am I at, or am I after the equivalence point, and what does that mean about my pH? Still want to keep in mind my buffer region down here, and that once I get past the equivalence point, I should have nothing but strong base left. Now it doesn't really matter what order we go in, so I'm just going to start with the first one, my initial pH. So let's go ahead. Just make some room for that guy. Here's a nicer version of my curve. I know mine was a little cramped up there. So if we correct this for our problem, that would be 250 at the equivalence point right there. We know initially we're just going to have a weak acid. In this whole region, that's going to be the buffer range. So that's when we should have a buffer. At the equivalence point, it's going to be somewhere above 7 because we only have conjugate base left. And then once we get past that, all we're going to have left is strong base. Life is going to be really easy. So the numbers here aren't necessarily going to match up. I just use this as a nice pretty picture because my drawing was not that great. So let's start with my initial pH. So initial pH is when we can just totally ignore this second guy. He doesn't do anything. Say, all right, we have 100 milliliters of HF, which is a weak acid. So this is just a weak acid titration problem. That's all it is. Now, a strong acid, life is really easy. Just negative log it and move on. Unfortunately, life is not that easy with a weak acid. With a weak acid, we need to make an ice table. So first things first, we write a reaction of our weak acid with water. Acids donate, so I'll produce F minus and H3O plus. I should be putting in all my aqueous and liquids here, but it's really hard to write on this tablet, and so I'm being a little lazy here. We should always include those when we're writing ours on our quizzes and exams. I'm going to cross out the water because he is a liquid, so I don't need him to make my ice table. I start out with 0.5 molar of the HF in none of my products. I'm going to use up some of this where I'm going to make my products here. So at equilibrium, I'll have 0.5 minus X, X, and then X. Meanwhile, I can write the expression for the Ka, which is going to be F minus times H3O plus, that should be an F up there, over HF. Now I can plug in everything I know. My Ka is 3.5 times 10 to the negative 4. And this is going to turn into x squared over 0.5 minus x. Now I make a little note that x is small, so I can ignore it right here. And now this just becomes a simple algebra problem. I multiply both sides by the 0.5 to move it over, and I square root that guy. So ultimately I find that x is equal to 0.013. And I go back to my table and I realize that what I really care about here is that that gives me my H3O plus concentration. Now that I've done that, pH is just negative log of my H3O plus, which in this case is 0.013. Oops. So my pH here is going to be 1.89. Of course, I always do my 5% check. So I put X, which is 0.013, over my initial concentration, which is 0.5, times 100%, and I get 2.6%. It's less than 5, so I was able to use my X is small approximation there. Always want to check my approximations. So this is just a weak acid titration problem. A weak acid pH problem. I really didn't need any other information. I ignored the NaOH completely. We knew how to do this back in chapter 15, so no problem whatsoever. So now I have my initial pH of 1.89. Makes sense. It's not crazy low because it's a weak acid, but it's still a pretty low pH. So now let's start adding some stuff. 100 milliliter solution. Now I'm adding 50 mils of sodium hydroxide. Keyword added. Whenever I add, I'm going to make my barf table. That's a B up there. So I'm going to make my barf table. I can cross out my water because he's a liquid, so I can cross it out just like in my ice table. So now I have to fill in what I start with. I began with just the HF, and I had 100 milliliters, which is 0.1 liters, and it is 0.5 molar. So if I do the math on that, I started with 0.05 moles of HF. Really, it should be 0.0500, but I'm kind of running out of space here, so I'm going to abbreviate. I didn't start with any hydroxide. I didn't start with any F-. So all I started with was the HF. Then I added the hydroxide. I added 50 milliliters or 0.050 liters of that, and he is 0.2 molar. So I do the math on that, and I added 0.01 moles of hydroxide. And so now I'm going to do the same thing I always do. I'm going to compare these two values and pick the smaller one, which in this case is the 0.01. So I'm going to subtract, and I'm going to have to add it to the product side, right? Because that's a product, my F-. So I'll end up with 0.04 of my HF. I won't have any hydroxide left, and I'll have 0.01 of this left. So now I'm going to think about if this makes sense. Remember, at the equivalence point, I needed to add 250 milliliters of my base. Here I've added 50 milliliters, so I'm before that in the equivalence point, or I'm before the equivalence point. So if I think about my curve, I should be in this region because I'm before the equivalence point, and that would be my buffer region. So just like I expected, I end up with a buffer. What I have here is a weak acid and some of its conjugate base, and that makes a buffer. So I always like to think about if I'm before, at, or after the equivalence point because it tells me what I should expect. Here I was before the equivalence point, which for a weak acid puts me in the buffer region. So when I look back, it makes sense. I have a weak acid and a conjugate base. I end up with a buffer. Good news is pH of a buffer is so super easy. We just use Henderson-Hasselbalch. We just use pH is equal to pKa plus the log of the base over the acid. So I need my pKa, really simple. My pKa is just the negative log of my Ka, which is 3.5 times 10 to the negative 4. It's going to give me 3.46. So my pKa is 3.46 plus the log. Now I need to put my base over my acid. So my base is the 0.01. My acid is the 0.04. And I can just leave them in moles when I plug this in. And so I just plug that guy into my calculator, and I get a pH of 2.86. So this makes sense. It's higher than my initial pH, which was 1.89. And it's in the buffer region, so it's not drastically higher, just 2.86. So far, it looks like we're going well. So we've gotten those steps. Now let's determine the pH at the equivalence point. Strong acid, strong base, life would be easy. We could just put 7. That's not the case here. So at the equivalence point, we've added, we know, 250 milliliters of NaOH. So we've added, let's make a BARF table in this case. We're going to cross out water once again. HF, we know from up there that we started with 0.05 moles of that. We don't have any of those. Now, I could do the math and figure out, okay, I have 250 milliliters and it's 0.2 molar, but at the equivalence point, what I know is that the acid and base are equal. So if I start with 0.05 of HF, I'm also going to add 0.05 moles of OH minus. That's the definition of the equivalence point. So now I subtract these guys, right? They're the same number, so I subtract both of those and add it over here. So I end up with none of those, and I've produced 0.05 here. So I've used up all my weak acid, I used up all my strong base, so all I have left is this conjugate base. So we say, okay, I've converted all of my weak acid to conjugate base. I have 0.05 moles of that. Well, how do I get a pH of a conjugate base? And the important thing to remember is this is really a weak base. So what I really need to do is an ice table. So with an ice table, we know we use concentration, not moles. So let's go ahead and get my concentration of that conjugate base. So I have 0.050 moles. I need to put my total liters on the bottom, so I started with 100 milliliters. At the equivalence point, I added 250, which means I have a total volume of 350 milliliters. Or when I plug it in here, that's going to be 0.350 liters. So my conjugate base concentration is going to be 0.143 molar. I also know that when I do this problem, I'm going to have to make an ice table, but since this is a base, I'm going to need his Kb in this case. I've provided with a Ka for HF, but F minus, he's going to need a Kb. So I'm going to go ahead and calculate that just to make my life easy. So the Kb is just 1.0 times 10 to the negative 14 over 3.5 times 10 to the negative 4. If you're not sure where I came up with that, it's because Ka times Kb gives me 1.0 times 10 to the negative 14. That's just a relationship we have. So we plug that in and we figure out that my Kb is 2.9 times 10 to the negative 11. So now I have my concentration of F minus and I have his Kb, so I can just do a regular ice table now. Now, I do want to point out, I did the trouble of this BARF table over here just for consistency. I didn't really need to. Knowing what I know about the equivalence point, I could have just said all of my weak acid is converted to conjugate base. So if I started with 0.05 of HF, I'll end up with 0.05 of F minus. But if I'm not sure, it's always a good idea to do the BARF table and you can see what you have at the end. And so it's just a nice visual reminder. And you're always doing the same thing so you get in a rhythm. So let's use what we've got here. So now all we're going to focus on, we don't have HF anymore. We don't have NaOH anymore. All we have left is this 0.143 molar F minus. So I'm just going to clear us up with some extra space here. I'll just remember those numbers. So we have F minus by himself. So the first thing we always do is write a reaction with water. F minus is a conjugate base. Bases accept. So that's going to produce HF and OH minus. So I'm going to make my ice table here. I'm going to cross out water. We determined up here that my F minus was 0.143 molar. So that's where I'm getting that number. And I don't have any HF or OH minus. So we do our usual minus X plus X. So I get 1.143 minus X, X, and X. Meanwhile, I can write an expression for my Kb, which is going to be equal to HF times OH minus over F minus. So I plug in my numbers. If we recall, we calculated my Kb. That's 2.9 times 10 to the negative 11. So I have 2.9 times 10 to the negative 11 is equal to x squared over 0.143 minus x. We do our usual x is small, so I can get rid of him. And now I just make it a really simple problem. I multiply the 0.143 over, take the square root, and I figure out that my x is equal to 2.02 times 10 to the negative 6. I go back to my ICE table and figure out which piece I really care about, which is going to be this one right here. That's really telling me my OH minus concentration. So that's the piece I'm going to use to get my pH. So I can't get pH directly. I have to start with my pOH. pOH, of course, is the negative log of the OH minus concentration, which is 2.02 times 10 to the negative 6. So my pOH is going to be 5.69. My pH, really simple, is just 14 minus that pOH. So my pH is going to be 8.31. Of course, we always do my 5% check. So x is 2.02 times 10 to the negative 6. I put that over my 0.143 times 100%. And that ends up being super, super tiny. I got 5 decimal places, so we see that that's going to be fine. I can't find my number right now. So, but in any case, if we do that, that number ends up being less than 5%. And so we find that this is okay. So after all that work, my pH at the equivalence point is 8.31. And if we go back to my original picture and think about it, that makes sense. At the equivalence point, we said the pH should be above 7, and that's exactly what we saw. So again, having this curve to refer back to, last time we knew we should be in the buffer region because we were before the equivalence point. This time we're at the equivalence point, so we can see that we should be above 7. So now we just have one last piece to do. So for weak acid titrations, this step is definitely the longest, but it's really not that bad. You just have to figure out your concentration of F minus, and then you can do a nice simple ice table problem. So last one, 100 milliliter solution. Now I'm going to add 300 milliliters of sodium hydroxide. Keyword here, of course, is added. So I'm going to do my barf table. Cross out my water, don't care about him. Going to do the same math I did before. I began with the HF, so we saw before that we just do 0.1 liters times my 0.5 molar, and I end up with 0.05 moles of HF. Don't start out with any OH minus or F minus. I add hydroxide, and this time I add 300 milliliters or 0.3 liters, and that's 0.2 molar. So this time I'm adding 0.06 moles. I always pick the smaller number. In this case, that's the 0.05. That must be my limiting reagent. So I'm going to react that much over here. I'm going to produce that much over here. So I'm not going to have any HF left. I'm going to have a little bit of this OH minus left. I'm going to produce some F minus. So when I look at this, I say, okay, I have a strong base and this conjugate base left. They're both bases. So to figure out what to do, we just have to remember that strong things always dominate over weak things. So if I have a strong base and a conjugate base, I'm just going to ignore the strong or the conjugate base. Chemists are terrible people. We ignore weak and small things. So I'm just going to focus on my strong base right here and proceed as if that conjugate base wasn't even there. Because the strong base, even though there's less of it, it's so much more powerful that that's going to take over. So, strong base, really easy. Get my pOH first. Just going to take the negative log of the concentration. So on top we have that 0.01 moles of OH minus, and on bottom we have to figure out my total volume. I started with 100, I added 300, so I have 400 milliliters total right now, or 0.4 liters. So I can calculate my pOH, negative log of that ratio right there, and I find that my pOH is 1.602. My pH, of course, is just 14 minus the pOH, so my pH is going to be 12.398. And this is exactly what we would expect to happen. We have a very high pH, which is what we should have. We're past the equivalence point. We only have base left, and so we would expect this really high pH. So again, just like in our strong titrations, start off the same way. Identify what kind of titration you have, sketch your curve, figure out for each step where you fall on the curve, and that's going to help you be able to check your answers and make sure everything makes sense.